All right, in this example, example 4, a particle moves counterclockwise around the ellipse with equation 9x squared plus 16y squared equals 25. And we've got some questions here. So since we're told that this is an ellipse, ellipses, in general, they can be anywhere. They can be elongated in any direction. They can be centered at the origin or not. But when an ellipse is written in the format ax squared plus by squared equals c, or a, b, and c are just real numbers, then the ellipse is necessarily centered at the origin. So therefore, we can quickly sketch this ellipse accurately by figuring out the x and y intercepts of this. So the easiest way to do this is to, well, x-intercepts are when y equals 0. Y-intercepts are when x equals 0. So if we find our x and y intercepts, the x-intercepts end up being 5 plus or minus 5/3, and the y-intercepts end up being plus or minus 5/4. Since 5/3 is a larger number than 5/4, we know that the spread in the x direction is longer than the spread in the y direction. So we know this ellipse is elongated in the x direction, horizontally. So we can go ahead and sketch this. And we don't actually need to label anything. We could if we so choose, but it's not necessary. I just wanted to know if I should sketch this being elongated horizontally or vertically. Okay. So now that we've got a representative ellipse, we are asked in which of the 4 quadrants is dx dt positive? Well, dx dt positive, well, if we imagine this as a particle moving around counterclockwise like this, then dx dt represents the rate at which the x-coordinate of the particle is changing. So if dx dt is positive, that must mean we're moving to the right, because this is the x direction. So increasing x is this direction. So moving to the left would mean dx dt is decreasing, that x is decreasing, so dx dt would have to be negative. Okay, so we can go ahead and label these quadrants. In quadrant 1, we would be moving like this. All right? In which case, dx dt would be negative. In quadrant 2, we're moving like this, so dx dt would yet again be negative. Now in quadrant 3, we are moving to the right finally. So in quadrant 3, dx dt would be positive, and again in quadrant 4, dx dt would be positive because we're moving up and to the right. So it appears that the answer is quadrants 3 and 4. 3 and 4. So now we're asked to find a relationship between dx dt and dy dt. Well, we know the equation of this ellipse is 9x squared plus 16y squared equals 25. If we go ahead and differentiate each side with respect to t, we'll derive such a relationship. This will be 18x dx dt plus 32y dy dt equals, derivative of a constant is of course 0. Now we can go ahead and simplify this a little bit more. We can go ahead and divide everything by 2, 9x dx dt plus 16y dy dt equals 0. Okay, there's a relationship. Part C, at what rate is the x-coordinate changing when the particle passes through the point 1, 1, if its y-coordinate is increasing at a rate of 6 meters per second? So the rate at which the x-coordinate is changing this is dx dt. And we are told that the rate at which the y-coordinate is changing, specifically increasing, that's how it's changing. So increasing rate means a positive rate. So we are given, so if dy dt at this point 1, 1 is equal to positive 6 meters per second, then what is dx dt? Well, we can go ahead and grab this equation from down here in part B and just fill in the information we know. So if we're going to go ahead and fill in what we know, to this entire expression, we are doing this at the point 1, 1. So we would have 9 dx dt plus 16 times 6 equals 0. And if we go ahead and solve this, dx dt, this should be equal to 32 thirds meters per second. Lastly, part D, we want to find dy dt when the particle is at the top and at the bottom of the ellipse. So if we just go back over here and think about our picture here, if the particle is going counterclockwise, then the top of the ellipse is right here, the bottom is right there. When the particle is at the top of the ellipse, can the y value increase more? No. It's going to begin decreasing. But if we think about this as a continuous process, which this motion is, in this portion, in quadrant 1, we know that the y-coordinate is increasing. So let's add this information. In quadrant 1, dy dt is positive, but then when we cross over into quadrant 2, dy dt is negative. So using ideas about continuous change, if the derivative is positive on this side and it's negative on this side, that means in the border, in other words, on the actual y-axis where the top is, the change would have to be 0, because we can't go from a positive value to a negative value unless we first pass through 0. That's just the intermediate value theorem. So we can say here, at the top, dy dt must be 0. And we can use the same argument for the bottom. At the bottom, dy dt must also be 0. And the explanation is just what we said. Let's just apply it to the bottom now. If we are in quadrant 3, this means dy dt is getting, y is getting smaller, so dy dt is negative. And then in quadrant 4, dy dt is positive because y is getting bigger. We can't go from a negative value to a positive value unless we pass through 0. Since there's only one location where we don't know about, it has to be right here. So 0.